Okay, super. So we are delighted to have Markus back to complete the second lecture of the two-lecture series on double parton scattering, and it was a great talk last week, and we're really looking forward to hearing what you have today. So please, Markus, when you're ready, take it away.
Very good. Thank you very much. Last week, I told you what double parton scattering is in the first place, why it is interesting. I sketched very roughly of what the experimentalists have achieved in that subject. And I started to develop the theory, starting from basics and going to more advanced topics. And then we had also many questions which pointed towards what I want to talk about today. So you can see kind of the menu that we have for today. We might not get to the very end of it, but whatever we see on the way should be worthwhile. So let's maybe start with a brief recap of what we've seen in the theory side. I've shown you that we have a theory description in the framework of factorization, namely factorizing cross-sections into double parton densities and parton level cross-sections. The parton level cross-sections are the familiar ones that you know from single parton scattering, and that also people have computed for single parton scattering. That's of course a great practical value that we can recycle many non-trivial theory achievements if we go to this double parton scattering game. The scale dependence of double parton scattering of double parton distributions, as I presented it last time, is again a very obvious analog of the D-Glub equations for single parton distributions. We'll see today where that becomes modified, but we're not there yet. Then we had some discussions about how do double parton distributions probably differ from just the product of two ordinary parton densities. If one makes the simplest assumption that the two partons don't care about each other, at least as far as their x momentum space dependence is concerned, then one gets a very handy formula. But we've also seen that formula is not very quantitative. It's good enough if you want an estimate and are happy with uncertainties of sometimes a factor of 2, maybe a factor of 3 or 4 in your cross-section estimate. But certainly not better than that. And certainly one should be open to surprises there if one goes to new kinematic regimes or new processes. So let's take a closer look at different types of correlations that the two partons can have. And here's the reminder. This is the cross-section formula we're discussing in a moment. Inside here is the DPD for one and the DPD for the other proton. So we are now focusing on what are these functions. There can be correlations between the momentum fraction dependence. Certainly, there must be such a correlation when the sum of the momentum fraction goes to 1, because that's the phase space boundary. The two partons together, of course, cannot take more than the proton momentum as a whole. And even if they approach 1, you expect these distributions to drop very sharply, just as the single parton distributions drop if their x value goes towards 1. Yeah, that's the analog of this here. But exactly how fast this vanishing is, we don't really know. And this would be very hard to get from experiments, because it would force you to make such measurements close to threshold where the cross-sections are tiny. This people could do for ordinary PDFs using deep elastic scattering. But for so complicated reactions like DPS, I think that's quite hopeless. But it's clear that in this regime here, the assumption that the two x fractions are distributed independently must break down. If one goes more to the valence region away from the limit, but in the region where each x is maybe around a third, you could try and see what do you get in a constituent quark model for the quark-quark distributions. And not surprisingly, people who did that exercise found strong correlations. That's quite clear, because the input in these models is a 3-particle wave function. So if you probe 2 out of the 3 particles in that wave function, of course you have all the rich correlations that you put into your wave function to start with. There's another type of correlation, and that is between any one of the two momentum fractions and the transverse distance. So here we can think, or we should remember that this distance variable here is the difference of the transverse position of one and the other parton. And the position of each parton by itself is meaningful because you can measure that distance relative to the center of your system, which is the proton. And if you remember what Barbara Paschini told you about in her GPD lectures, you can actually formulate single parton distributions as distributions in X, the usual momentum fraction, and the impact parameter or transverse position of that one parton relative to the proton center. And the Y is then just the B of the first minus B of the second parton. Now, what we know from the impact parameter distributions of single partons, they can be studied in processes that involve GPDs. And a very nice process for that purpose is the exclusive production of DESY mesons that has been measured with very high precision in the transverse momentum spectrum at Hera, so small x values. And there, the measurement found that if you convert that transverse momentum spectrum of the scattered proton by a Fourier transform into an average impact parameter squared, that was sensitive to the x values at which you probed the gluons. And they found this parameter, which people from the older generation also in the notation will recognize as what sort of 50 years ago was called shrinkage. So it describes that the proton transverse proton size, in a sense, or more precisely here, the places where you find gluons, that size changes if the gluons have changed their momentum fractions. And in these units, you see for 1 unit in log of the momentum fraction, that's a sensible change. Yeah? 0.16 femtometers is something that's comparable to a fraction of the proton size as a whole. Yeah? So there is some indication that the X and transverse position spectrum of a single parton know about each other. And if you have then a double parton distribution, it would be very strange if that kind of correlation didn't also show up there. Actually, since these experiments and their meaning was known for quite some time, people have used this knowledge and put that into their models of double parton scattering, especially these last two works here. They used Monte Carlo generators, and they found if for their Monte Carlo generators MPI model, multi-parton interaction model, they allowed such a correlation, it did improve the description of certain observable quantities. That was quite a nice work, but it hasn't really been followed up in a systematic way ever since. Let's go to another kind of correlation, and that concerns the quantum numbers of the two partons. Now, if you look at a single parton in an unpolarized proton, its polarization doesn't matter because of parity invariance. Yeah, so in an unpolarized proton, you cannot see a polarized single parton. However, if you look at two partons coherently, then their neutral spins can be correlated even if the proton is unpolarized. And the correlations can be in all kinds of allowed polarization states. So for quarks, you have longitudinal or transverse polarization correlations, and for the gluons, you have longitudinal or linear polarization. It doesn't take much to include that physics in the formula. You just have to augment your labels for what the partons are with extra labels for what their polarization is. And of course, you have to know what are the distributions for the polarized two parton systems. And I told you we don't know terribly well their unpolarized versions, so you won't be surprised if I tell you we know even less about the polarized ones. What people have looked at some time ago was that if you assume such polarization correlations between two partons, that would induce observable consequences in DPS cross-sections. For gauge boson pairs, that was realized early on. And it's not surprising at all, because if you produce a W boson is extremely picky about the polarization of quarks it couples to. Namely, it doesn't couple at all to right-handed quarks, and therefore it is very sensitive to the quark polarization in the initial state. And no surprise, you find that again in the cross-section predictions. So it was also looked for double charm production, where you have polarization-dependent cross-sections from gluon going to charm. If there were such correlations, they would show up in observables. You can then again try your models. In an MIT back model, people did see large correlations between two quarks. Something surprising we saw in a study in lattice QCD some time ago was that the polarization correlations we looked at there were typically quite small, and much smaller certainly than what you would expect in a naive three-quark picture with simple three-quark wave functions. So that was a surprise, and we don't have an explanation. As usual, if you do a lattice calculation, it tells you something about nature, but it doesn't necessarily tell you why things come out the way they do. Now, that lattice study was basically probing moments in X, or integrals over X1 and X2. And these are, of course, dominated by average values of the X's. So none of these two studies can tell us anything about the size of spin correlations at lowish values of X's, which are the ones that we most easily probe in the experiments. So we really don't know. The one thing we know is that if you have some size of correlations at a low scale between the two parton spins, and you evolve the distributions with the Diehl equations to a higher scale where your measurement takes place, then the correlations tend to be washed out. And that's easy to understand. Unpolarized densities, especially the unpolarized gluon distributions, they shoot up. They increase very strongly if you increase the scale. That's sort of the starting, one of the starting points of small X phenomena. But if you look at a longitudinal gluon polarization, the polarized gluon distribution doesn't shoot up so much. It's very lazy in its evolution. And that means the correlations, which are the polarized, basically the polarized compared with the unpolarized distributions, they become small if you go to larger scales. And that we could see also quantitatively. So you would need very large initial scale correlations to still see effects once you go to the scales of the measurements. But that was taken into account in these studies here, so they're not invalidated by that. It just means it's hard to detect such spin correlations if your measurement is taking place at a very high scale. Now, the last type of correlation I want to speak of, and this here is an equalizer. We'll come back to it later. Yes?
Sorry, just before you go on, if you could go back one slide, please. Maybe this is just a dumb question, but I expected the gluon polarizations to be the two transverse polarizations, so I'm surprised it's longitudinal and linear. Am I thinking something strangely here?
No, it's the polarization of the gluon. It's not the direction of it's not the direction of the A field. So the description of the gluon polarization is really the density matrix of a spin 1 particle, the spin density matrix, and that has a longitudinal part and a linear polarization part.
Okay, so maybe I'll ask one follow-up question, and then maybe I'll follow up offline. Yes, gluons definitely are going to be helicity 1 particle, so I'd expect plus and minus helicity.
Yes, so I can rewrite the statement of longitudinal and linear polarization for the gluons in terms of helicities. Then longitudinal means you have the same helicities on the two parton operators, or the two parton legs, and you look for the difference of both helicities being positive or both being negative. And the linear polarization corresponds to the helicity flip, where you would have a positive helicity here and a negative helicity there with a helicity difference of 2 units.
Okay, super. Thank you very much.
So that can be rewritten in terms of linear polarization for the polarization vectors.
Okay, very good. Thank you.
But of course, the polarization vectors are always transverse in that sense.
Yeah.
I could say this is the nomenclature that is known from optics for the photon polarization.
Right.
Okay, I'm just getting a message. My internet connection is unstable, so I'll plug in the Ethernet. Just give me a second.
Okay.
Hope nothing bad happens now. Let's see.
You're still there, so yeah.
Good.
Yeah.
So let's.
Takes a second. Exactly. Now is it gonna kick over to? You're still there, Herbert? Yes. Oh wait, there we go. Good. All right. I think we're back.
Okay, very good. So something that might be interesting if one has a model of small x physics that allows one to compute something like polarized quark distributions. Would be interesting to see what you get for the 2 particle correlations inside an unpolarized proton. So now there is another quantum number, which is sort of the quantum number that makes QCD being QCD, and that's color. So the color of the 2 partons, the 2 quarks or the gluons, can be also correlated. So what we discussed, well, what basically, without saying it, I had in mind so far is it was assumed that the color state of the first proton is summed over. So that means you take the same color state, the same color index for this field and the field in the complex conjugate amplitude, and you sum over these. And you do the same for the second parton. That's what you also do in single parton densities. But that's not the only way to combine these 4 open color indices here. You can also have the color state of this one correlated with the color state of the other one. And that's what I mean by color correlations. And that is, again, a phenomenon which can be incorporated in these distributions. We'll see that later. You just get extra labels on the distributions and extra distributions that describe the different ways of combining the color states here. And that will, again, have to be folded into. And then you will also need the sub-process cross-sections for different possibilities of the color of the initial state partons here and on the other side. That's very simple if you produce color singlet, because that just means the color of this parton has to be the anti-color of the other one. But if you produce, say, jets, which themselves carry color state, then this becomes a bit more complicated, but it's all feasible. Now, we will see later, hopefully, that if you include this color dependence in the DPDs, then the evolution equations are modified. And they are modified in several ways and interesting ways, and we'll see that. Very important from the practical point of view is that the case where the color of these partons is correlated, by that I mean it's not summed over individually, the contribution of that to the cross-section is suppressed by Sudakov double logarithms. And those of you who have seen Sudakov logarithms in other applications know that Sudakov suppression can be very strong. We're talking about orders of magnitude even. And if that's the case, obviously, you forget about these color correlations. Very roughly speaking, how do you expect to get such Sudakov logarithms? For those who have sort of looked at such things, the first argument for that was done in the early days, and the observation was, well, let's see if I start decorating my tree level graph here with gluon emission. I can have a virtual gluon correction, which would be, for example, at this vertex here. That doesn't count about how the color of the other partons is coupled, because it only sees the color of this of the particles entering this vertex, and that's fixed and doesn't care if you put a gluon on top. However, if you have a parton emission, say between here and it's the parton, the gluon is emitted here and caught up here, or it's emitted here and caught there, then the color factor of that Feynman graph will depend on how the color of these two legs is coupled. And therefore, for the real emission graphs, your color factors change. Now, you probably know from your lectures that if you compute radiative corrections, you have a cancellation of soft singularities between real and virtual graphs. Now, you take your real graphs and change their color factors, but not for the virtual graphs, and that's clear. The cancellation of your soft singularities will be broken. Then you have to see how to get rid of the singularities, but what is left over then turns out to be these double logarithms order at each order. It's a squared logarithm, and resumming them to all orders can give you these strong suppressions. So a first quantitative estimate of that suppression factor inside a DPD was given by Manohar and Vallabhai some years ago. Well, it's even a decade, time flies. Mm-hmm. And you see, depending on the final hard scale with two versions of approximations, don't worry about that here, you find for a sort of electroweak physics scale, you can forget about color correlations because, I mean, I can't even read off how strong the suppression is here. If you go to, say, a hard scale of 10 GeV, charm physics, the suppression, it's a factor smaller than 1, but it's not tiny. But it turns out this is actually too simple for a very tricky reason, and that we will understand later. So for now, let's leave this aside. We'll come back to it when we have seen other things. Now, so far I've discussed this interparton distance. It's an important part of the physics here. Let's look into a corner of phase space, so to speak, and look at the region where this parton distance is small compared with a non-perturbative scale. So small compared with 0.5 femtometers or so. In that case, you can appeal to perturbation theory because the coupling is small at such distances. And if you ask, how do can I get two partons at a relative distance of 1/10 or 100th of a femtometer? Well, the kind of obvious answer is start with a single parton and split it into two. If this is perturbative, then the distance here is going to be small. And if the distance is small, the coupling is small, and you can compute this reliably. And indeed, that argument can be formalized, and one finds that, yes, the leading contribution at small parton distance comes from starting with a single parton and splitting it into the two partons that you observe. If you go to higher orders, you can also, the splitting can go to more than two partons, but only two of them are observed, and the third one is kind of part of the unobserved initial state. Now, this mechanism gives very strong correlations in everything. A nice example for that is if you have this splitting of a gluon into a quark-antiquark pair, just from the way that a gluon couples to massless quarks, you know that whatever the helicity of the quark is, the helicity of the antiquark is minus that. So you have minus 100% correlation between the longitudinal polarizations here. Strongest correlation you can possibly have. And if you work out the color factors, you also find that the color correlation between these two partons is significant. So this looks very nice to the theorists because the theorists can now say, oh, at least if I'm at small y, I can compute my DPDs in terms of simpler quantities. And the formula is it's a splitting function that describes this vertex or its higher order analogs. down here you have a single parton that's described by one of the normal PDFs, which we know fairly well. And you can just easily see for dimensional reasons, since this here is a distribution, a density in the area y squared. You see that, for example, here. The mass dimension of this here must be 1 over area. And the only area you have in this computation is y squared. And that tells you if you go to small y, this here definitely grows very fast and becomes dominant. So you might think you're happy, but your happiness doesn't last for long, because the moment you put this into your cross-section formula here, ouch, you have d squared y over y squared times y squared. And that's a terribly divergent integral in the small y region. So we are kind of used to logarithmic divergences in QCD. This is not even logarithmic. It's a power law divergence. And as usual, if you find a divergence in a theory calculation, normally the reason is that the calculation is right, but the thinking behind it is wrong. And that's what is the problem here, because this formula is not even valid if the distance between the partons becomes of the order of 1 over the hard scale in the hard scattering. And why is that? You can see that from a different point of view. This here is my graph for the double Drell-Yan process, where for each of the two DPDs, I've looked inside, taking small y, and then I have this splitting process. So I've just copied this graph here for both protons. So this here is now the graph for my double parton scattering at small y. Now, if I take away these boxes, I get this graph. You show this graph to anyone you meet on the street, and they will tell you, yeah, of course, that's a double box graph for single parton scattering, gluon fusion into 2 bosons. And the well-informed people will tell you, oh, by the way, that's been computed a long time ago. So what looks like double parton scattering here is actually single parton scattering. So what can we make of that? And people actually realized that earlier, even outside the DPD community. But kind of that in the early days was a real problem when it became clear. First of all, the cross-section formula for DPS is giving you a singularity. And anyway, you have double counting. So what's the solution? Physically, the solution is relatively clear. When does it make sense to speak of 2 hard scatters from 2 partons? That makes sense if the typical size scale of the hard scattering is small compared with the distance between the 2 partons, because then you can say one scatter is here, another scatter is there. Now the scatterings are not quite point-like in some sense, and that sense can be made precise if one wants to. The typical size of the hard scattering can be thought of as 1 over the hard scale. And if that size becomes of the same order as the distance between these 2 partons, then it makes no sense to factorize this process into 2 hard scatters and 4 splittings, because all these things take place in the same physical area, and the proper description is with this box graph here. If, however, y is much smaller than 1 over q, then this here is the correct description. Since we know in this description we can actually resum large logarithms from higher orders by using the D-club equations, you gain something at small y if you use this DPD description rather than computing your hard scattering, because here you can go 1 order higher. You could have 1 gluon between here and there, but then it stops because these higher order calculations at some point become incredibly complicated and lengthy. But we have to somehow get these 2 things under one roof, and that took us really quite some time to figure out. And some years ago, we proposed one solution, which we think has a number of advantages, and I want to briefly sketch that to you here. So what's the solution? The solution comes in two parts. First of all, we need a double parton scattering cross-section that's finite. And sort of, I can tell you, we hesitated long before we wrote this down, because in a sense, it looks too easy. I argued you shouldn't use this formula if y gets of the order 1 over q. So you can cure that by saying, well, I put a cutoff here on the y integration from below. And the cutoff scale, if I write it as a momentum scale, should be of order of the hard scale q. Or if you have two hard scales, you should take the smaller of the two hard scales. Now that looks like maybe not very elegant, because cutoffs kind of have a poor reputation sometimes. But it turns out this kind of cutoff is really harmless. It doesn't break any symmetries that you haven't broken anyway. And there's nothing wrong about it. And it turns out to just work. And when we do this cutoff, it's understood that our parton distributions here, our double parton distributions, include everything that QCD wants them to include. That is the splitting, and also the contributions where you don't think of the two partons coming from a single parton, but from two partons in the original proton wave function, because you really have both possibilities. That is good if you want to keep connection with QCD as a field theory, because I told you DPDs can be defined as operator matrix elements. If I were to say, okay, let's take out the part of this DPDs that comes from a parton splitting, I don't even know how to formulate that in terms of operators. And at the very least, I would have to create a terrible mess in my definition if I wanted to exclude the parton splitting from the DPDs, so we never tried. So that looks like a simple solution. It gives me a finite value for DPS, but what about the double counting problem? Well, that is solved in the following way. Write the full cross-section as your regularized double parton scattering cross-section plus the full single parton scattering cross-section, which you have to add anyway, and that includes at higher orders, also these double box graphs. And since there is a double counting between here and there, subtract something that removes that double counting. Sounds easy, you just have to figure out what the subtraction term should be. And it turns out the subtraction term has a very simple algorithmic construction. It says, just take your DPS cross-section formula and instead of the true DPDs, put in there just what you get from a single perturbative splitting at fixed order. Kind of put in there what is in this boxed graph without any higher order decorations. And by the way, that is a computation which is much simpler than this higher loop computation for single parton scattering. So I'll tell you why that works in a second. But first of all, a good feature of this construction is if I can compute this one, it's even easier to compute the subtraction term. And I can reuse the single parton scattering from conventional calculations without having to open these box graphs and subtract anything complicated from the higher loop calculation. Because that would be the last thing I want to do, namely to go back to complicated 2 and 3 loop calculations and having to modify them. Yeah, that means you're immediately in for several years of work. No, we don't do that. We don't touch this. We'll remove the double counting, not by opening this here and doing something complicated, but by subtracting something that's constructed in a simple way. And from a physics point of view, this scheme defines what you mean by double parton scattering, how you delineate it from single parton scattering, because the discussion I've given here really tells you, in an absolute sense, you cannot say whether in a given kinematic configuration you have single or double parton scattering. It's a matter of definition. As so many things, even if you go back to factorization, what you put inside your parton distributions and call proton structure, and what you put in the hard process depends on the factorization scale. And if you change that, you change what you mean by parton structure. And the same story holds here. Oh, just to mention, there is also a hybrid situation where you have a splitting on one side for one of the protons, but not in the other. Then this type of integral here is still logarithmically divergent, so it still needs a double lower cutoff. So I've now written this here as a subtraction term for the one parton versus one, and another one for one parton versus two, with a splitting only in one of the two protons. And what is the thing that you have a double counting against here? Well, that's what would be computed as a cross-section with a twist 2 distribution in one of the two protons and a twist 4 distribution in the other one. Now, that's truly an exotic kind of thing. It's clear what it should be in principle. In practice, nobody has ever computed this. I think it could be computed for such a simple process, but for more complicated things, that would be very difficult. So I'm saying in principle, you can also include this here. In practice, I would hesitate to do it. The good thing of this construction is if you leave out this term here because it's too difficult and hard for you to compute, if you include this one here, you can show that you catch at least the leading logarithmic part of this graph, which is built up from the region where y is much smaller than 1 over q. Since it's a logarithmic integral, dy squared over y, you know that the most important contribution of it comes not from the extremes, the lower or the upper boundary, but sort of from the region in between. And this is where the double parton scattering description is already good. So why does this subtraction formalism work? Let's see how it works. For that purpose, so this is now meant to represent my double parton scattering formula at small y, where you have a splitting. And this is meant to represent the single parton scattering two-loop calculation. I showed you in the last lecture that while you would naturally do such a computation in transverse momentum space, you can make a Fourier transform of these transverse momenta, and then you can get this variable y into the game. Yeah? So even in this loop graph, the variable y has a well-defined sense. It's just Fourier conjugate to one of the loop momenta that you're supposed to integrate over. So can be done. And for the argument I'm giving here, you should think of having done it. So now if the distance y in this or that graph is of the order of one of the hard scale, then it turns out your DPS term is basically equal to the subtraction term. Why is that? Because the perturbative calculation of the DPD, which I'm using in here, is a very good approximation to the true DPD that I put in there. And then I subtract something basically from itself. And if these two things cancel at very small y, then the thing that's left over is single parton scattering. And that's exactly what we want from the physics point of view. Now, if you go to the region where y is much bigger than 1 over q, turns out then the subtraction term is approximately equal to this term. And why is that? Well, if the distance here is much bigger than 1 over q, then all the approximations we make in order to get the double parton scattering cross-section formula are good approximations. So you can then say, well, I've just rewritten my perturbative graph in a clever way that gives me the description in terms of a DPD. And that means if these two things cancel, then the true DPD term is the one that's left over, and that is what you want. And the same argument can be given to this hybrid 2 scattering versus 1 that I mentioned earlier. And it can be also shown on more general grounds that this kind of subtraction construction works not only with the tree-level graphs, but also order by order in perturbation theory if you go to higher orders. So this has a practically important consequences, which I want to briefly sketch, and we come hopefully back to it later in the talk. We now have two perturbative ingredients excuse me, in computing double parton scattering. One of them is we have at small y perturbative initial conditions, and we have the perturbative evolution of the double deglubbed type, a deglub evolution for each of the two partons after the splitting. Now, the natural scale at which to evaluate this formula here, as usual, if you do fixed order perturbation theory, is you should take the natural scale of the problem in order to avoid large logarithms from higher orders, because then your perturbative expansion isn't good, and truncating it gives you no good results. So the natural scale here is 1 over y. And what you can then think of what the deglub equations do. I assume you know that deglub equation or deglub evolution, graphically speaking, resums ladder graphs to all orders. So we have deglub evolutions in different places in this graph. Not shown here is you have here ordinary parton density that is, of course, evolved up to the scale mu equal 1 over y. 1 over y is the scale of the momentum scale typically of this splitting. So you have ladders between the initial state parton pair that are resummed inside the PDFs. Then you have the splitting at a typical scale of 1 over y. And after the splitting, you have deglub evolution for the double parton distributions. And that resums ladder exchanges between the two partons after the splitting, either this parton pair or that parton pair. So you see that this DPS construction has a much richer structure in terms of resumming large logarithms than the single parton scattering graph, where you would just resum the ladder exchanges from the initial scale, from the initial conditions, but you would not resum any of these ones. And in the single parton scattering region, where y is of order 1 over q, that's exactly what this construction tells you. Because if the splitting is of order 1 over q, then there is nothing left to evolve to, because 1 over q is your final scale in the equation. A practically important point is the following. You can imagine quite easily if a single parton ladder tends to make your distributions bigger, having 2 of them after the splitting makes it bigger much faster, basically twice as fast. So if you have a lot of evolution path between 1 over y and the final scale q, that can become enhanced, that region. And that enhances this region where DPS is an appropriate description of the physics. And we've seen that in the numerical studies we've done, whereas naively you would expect that the splitting at small distances here should dominate. If you put in enough phase space for evolution, DPS can actually be enhanced quite a bit. And that's, of course, an interesting thing. So let's leave that where it is and come now to something which I promised Will last time to show you at least a slide on. And that's going back to the theoretical underpinning of all this, which is the factorization formula. So here's a sketch of what can be done. And it's really modeled after what has been done in the 1980s for single parton scattering, especially for the single Drell-Yan process. So the basic steps are very similar in the two cases, only that some stages of the steps are not surprisingly more complicated if you have twice as many partons around. So the first step is sort of represented in the left-hand side here. you identify, you think of your overall reaction for the cross-section here, so here's the final state cut, as a big graph with a multi-scale setting, and you identify leading subgraphs and momentum regions. And this kind of identification of leading momentum regions inside a graph is based on power counting or dimensional analysis, and that was pioneered by Libby and Sturman. So that was the keyword that also Will mentioned last time. And you find then that for double parton scattering, a leading momentum region is when you have collinear partons from each of the two incoming protons merging in a hard scattering, giving you the final state for one and for the other of the two particles produced. And on top of that, you have soft gluon exchanges between the spectators in the two hadrons which collide head-on. These are spectators in the sense that they don't care at all about what happens in the hard scattering processes. So this is a very complicated set of graphs. Then you can simplify that step by steps. You can have collinear gluons here along, any number of them, along with the incoming quarks, say. And you can recast these gluons into Wilson lines. And these are exactly the Wilson lines that appear in the operators that define our DPDs, or that would define a PDF if you had a single hard scattering. If you have these soft gluon exchanges here and there, they are soft gluons coupling to very fast moving things in one or the other direction. And these soft gluons can be decoupled by an approximation, which for the experts is called the Eikenel approximation, which people doing small X scattering know very well because it's their bread and butter in a sense. After this decoupling of the gluons, they don't care about the details of what they coupled to. They care just about the overall color structure. Now that's a nice physical statement. Soft gluons, when they couple to fast-moving color charges, don't care about what the color charges are in detail. They just care about the net color charge. And that net color charge can be represented by Wilson line operators again. So in here you have a matrix element in the vacuum between as many Wilson lines as you have incoming partons in the original process. So you would have 2 times 2 Wilson lines for single parton scattering, and you have 4 times 2 Wilson lines for DPS. Oh, that's quite a beast here. We'll come back to that later. But at least we've decoupled this beast from the structure of the incoming protons. That's a good step. And in a sense, the hardest and most hairy part of a factorization proof for hadron-hadron collisions is to show that so-called Glauber gluons denote gluons which are exchanged between the between the spectators, but which are in a momentum region where this coupling here cannot be shown. So in order to have this decoupling here, you need a certain condition on the momentum regions of the gluons. Glauber gluons are the gluons that are not in this momentum region. So they keep tying together the two protons. And the fact that their effect cancels is really very much tied with the fact that you sum over all the unobserved final states. Remember, that was the basic discussion I gave at the beginning of these lectures. Any factorization formula that we are discussing here works only because you sum over unobserved particles, especially the ones that are in the spectator regions of the two hadrons. And only because you sum over these details of the final state can you show that the effect of the Glauber gluons, which tie these spectators together, these effects are there physically, but their net effect on your observable is not there. And just a technical remark, you will not be surprised if I tell you that to show this Glauber cancellation in the presence of two hard scatters, each of which has its own complicated color structure, looks terrible even compared with the case of single parton scattering, which was difficult enough. The only way, and we really struggled for years to find the answer to that. Do these exchanges still cancel if you have two hard scatters? The key technically to showing that was to use not Feynman covariant perturbation theory, but light cone time ordered perturbation theory, which incidentally is also the most elegant way to show the same kind of Glauber-Gluon cancellations for single parton scattering. So that's the wrap up of a long story. And once you've done that, so you have this side of the equation, there's still one step to go. You have this soft factor, which is a vacuum matrix element. That's as much a non-perturbative object as the TMD, the DPDs are, in order to limit the number of unknown perturbative functions in your final result. It's useful to kind of split this soft factor into two pieces and assign half of it, loosely speaking, to this DPD and the other one to that DPD, because the DPDs are anyway non-perturbative. So you might just augment them by having some other non-perturbative physics inside them. And that's indeed what one does for single parton transverse momentum distributions, if you have seen these before. I will draw analogs with transverse momentum distributions, dependent distributions of single partons, which would, for example, allow you to compute the transverse momentum spectrum of a Drell-Yan Z boson. So this is very important at the LHC. If you haven't heard about this, then just ignore it for now, because I won't have the time to explain it. The upshot of this, once you have absorbed half of this here and half of this there, you have really the factorization formula that has been the basis of my discussion in these lectures. And I told you all this not only because Will was curious to know about it, but also because this becomes important if we speak about color structure. And that's the last part of these lectures. Now, time is running up. Let's see how far we get. So let's take a closer look at this object with 4 open color indices for the 2 parton pairs we have in the DPD. The idea is to sort of order this color dependence by projecting the pairs of partons that belong to the same momentum fraction, to the same parton that enters in the first or into the second hard scattering pairwise. And you can project these 2 color states on a representation of SUN, of the color group, SU3 if you like. That's the same kind of algebraic exercise you would do if you couple the spins of 2 particles, say coupling 2 spin 1/2 to a spin 1 or spin 0. So if you have 2 quark legs, then you have 2 possibilities of coupling their respective colors. One is the singlet. That just means sum over, set these 2 colors equal and sum over them. And that's exactly this non-color correlated case I've discussed before, the simple-minded one, as you would do in the PDFs. But you can also couple this to an octet. And technically that you do by multiplying these 2 color indices here, oops, sorry, with not the Kronecker delta in the colors, but with one of the generators of the color group. So that has 2 indices to saturate these quark color indices, and it has an open color index in the octet, which just reflects that you've coupled these guys to an octet. If you couple these guys to an octet too, then you have 2 octets, and you know that you can couple 2 octets to a singlet by just summing over 2 octet indices, and that's what is done in here. So we have 2 different color representations for quark DPDs. For gluons, it's a bit more complicated because coupling 2 color octets to irreducible representations has a number of different possibilities. So If you haven't seen that, it's actually a nice part of SU3 group theory, and you could revise it afterwards. So what you get is two octets. One is antisymmetric, one is symmetric. This one comes with the F-ABC tensor, this one with a D-ABC. Then you have a decuplet, an antidecuplet, and a 27 representation. And if you add up these numbers, you get 64, and that is as many states as you have with two octets. So everything is right. So the notation for these DPDs is now that we have to specify on top of everything else the two-color representation of the first and the second parton. What is clear is that the dimension of these two representations has to be equal, because otherwise I cannot couple them to an overall color singlet. And this I must, because of course, taken all together, these four lines cannot take net color charge, because you come in with a proton, you go out with a proton, and that means whatever you have here in the T channel must be overall color neutral. Nice thing about this representation is, if you now consider D-club evolution was about ladder graphs, ladders that tie either together these two partons or those two partons. That means if you just put as many ladders here or there, you don't change the color state of the upper lines, because color is conserved. And that means different color combinations of these guys do not mix under renormalization. Otherwise, it would be a much more complicated problem. There is an interesting pattern of flavor mixing for the octets. You can have the symmetric gluon octet. That couples to the sum of quark and anti-quark distributions, because you can have two gluons going into a quark-antiquark pair. And that's the kind of coupling you know from the color singlet. A gluon under evolution mixes with the sum of quark and anti-quark distributions. However, you also have an antisymmetric octet that has the opposite charge parity, turns out. So this kind of thing mixes under evolution with a difference of quark and anti-quark distributions in the octet, and that's a kind of amusing new ingredient here. But straightforward to handle, so no problem. Now we have projected the color of these parton decks in the DPDs. We should also do the same for the color indices of the soft factors that these DPDs are related with, in the sense that you can guess from this graph here. And here you see, if you have, for example, the color octet, you would have a Wilson line here. Then you put on your color octet projector, TA, and here you have the conjugate Wilson line, just because this is in the amplitude and that is in the complex conjugate amplitude. These Wilson lines are sitting at the same transverse positions as the respective partons, so they're sitting at the same point in space. And if you have W times W dagger with a unit in between, then you have F1. And that means in the color singlet, this soft factor just becomes unity, then you can forget about it. But in the color octet, this is of course no longer unity, and that means the soft factor is not equal to 1. And this physics of the soft factor is related with a dependence on the rapidity of the gluons that are inside these graphs, and with the Sudakov factors that I mentioned before. So people who know TMD factorization know that you have these soft factors and that they describe Sudakov suppression. And the same thing happens here, even though you haven't measured any transverse momentum in the final state, but you have a transverse distance in the game because you have two partons that are sitting at a relative transverse distance. So we're running out of time. How much time will you allow me to go over time?
I think if you can get to a good stopping point, that would be great.
Okay, then let's do that. So this soft factor looks like a terribly complicated beast, but it has a number of simplifications which come from very nice relations between Wilson lines and color representations. I will skip over this and instead show you what the upshot of the argument is. So if you have non-singlet color representations here, you have to really incorporate the soft factors. And the soft factors, when you split this overall soft factor into two pieces that you assign to one or the other of the hadrons, remember that's what I said before, then you have to specify how do you split this into two pieces. And the natural way to do that is to say, well, all the part of these soft gluons that has the soft gluons going more or less in the direction of this proton go down here, and all the gluons with a rapidity that is negative are put into the DPD for the negative rapidity proton. And that splitting is described by rapidity, and that rapidity is just related with the log of this parameter, which is conventionally defined to have a mass dimension. So in a sense, this just tells you where do you put the soft gluon exchange to assign it to one or the other of the two distribution. And the nice thing is if you have that, then you have a set of evolution equations. One of them is in this rapidity parameter. So you have a logarithmic derivative or a rapidity derivative of the distribution here. And the people who do small x physics amongst you will, of course, know that there are such evolution equations in rapidity. This one is of the type of that was discussed by Collins and Soper for TMDs, which, as I said before, have a close formal relationship with this physics. And this kernel that describes the rapidity change has itself a scale dependence that is given by a simple RGE. This is a closed system that has an easy solution as a differential equation, which I will not write down. And it's well known from the case of transverse momentum distributions, where everything is the same, basically just that you have fewer indices because you have just one parton instead of two. The D-glub equations, which I had discussed before, now look like this. Scale derivative with respect to one of the parton scales is given by a splitting function convoluted with the DPD. That is the same kind of thing you would have for PDFs, again with fewer indices. But the new part here that comes from this anomalous dimension of your rapidity kernel, that gives you an extra contribution that was absent before. And if you start looking at this differential equation, you find, aha, if I just solve it for this part, ignoring that part, I get double logarithms in an exponential, and that is precisely the Sudakov factors I was discussing before. And that allows us in a quantitative way now to rediscuss the problem of Sudakov suppression for color states. So that's what's written here. And let me skip over that. The nicest way, perhaps, of showing this Sudakov suppression, let me discuss it here, is to show the Y dependence of the double parton distributions. Here it is at the scale where we have the initial scale. That's basically the 1 over Y, if Y is small, because that's what I explained to you. That's the natural scale of the splitting. That's where you want to initialize your DPDs and compute them by splitting if Y is small. If Y is large, you have to make a model, which is what we did here. So here you have the different curves for different color combinations of the two gluons in my example. And it's just the splitting part here. It's the non-splitting intrinsic part, which we modeled here. So this is rather flat at low Y, and then at some point it drops. Now, if you turn on evolution to some final scale here, it was 80 GeV, that would be the scale relevant for W production. You find at low scales, notice that the number of orders of magnitude here has changed drastically. At low scales, not much has happened. And the color non-singlet pieces in the symmetric octet or the 27 are basically as big compared with the singlet as they were in the initial conditions. No suppression here. And that's simply because in this region of small y, you don't have much to evolve between the initial 1 over y and the final scale. At this point, you don't evolve at all. So this is very natural. And it quantifies the statement I made before. If you go to very large Y, then this Sudakov suppression kicks in, and you see these colors, non-singlet distributions drop like a stone compared with a singlet. And therefore, it becomes unimportant here. And this is the kind of strong Sudakov suppression that people had in mind before, even in the 80s. That was also this plot I showed you before. That kind of discarded the possibility that you circumvent the Sudakov suppression by having a parton splitting here at a certain distance y, which is much closer to your final scale than the non-perturbative intrinsic scale of the proton. And if you put all this together now, if you multiply, say, this distribution with that one and integrate over all y, you find you get quite some contribution from not so small y, not so large y, and therefore the net contribution to the cross-section of these color combinations can be noteworthy. It's typically still suppressed, but not by factors of 100. And that's because of the interplay of the perturbative splitting with the Sudakov suppression and evolution. And then I would like to wrap up. There are some more plots. If you have time, you can look at them afterwards. Here's my summary. The nice, in a way, interesting thing about double parton distributions is that they allow us to quantify many interesting correlations between two partons inside a proton. At small y, we have a perturbative splitting mechanism that we can compute, and that shows us there are strong correlations, not surprising. This splitting, however, leads to a double counting problem, which you have to come to grips with, but we've shown they can do that with a cutoff and a subtraction procedure. And finally, whereas it's true that color correlations between partons are generically suppressed, they're not so strongly suppressed as one might naively think. And that means in the end of the day, for a reliable phenomenology, one should take them into account whenever it's technically possible. And with this, I thank you for your time and attention.
Okay, super. Thank you very much. That was very nice. Do we have questions from in the room? Yeah, Daniel, please.
I have one, but I think it might just be something that I don't understand. When you're talking about the cancellation of Wilson lines, you spoke about in the fundamental representation, you have two Wilson lines at the same position and it cancels with the complex conjugate, but its adjoint wasn't in the adjoint representation. Why is that?
I couldn't hear you very well because there's just a plane flying over my head here. So the question is, if this here is a fundamental representation Wilson line and that it's its conjugate, and if I replace the t with a 1, why is that not unity? Or?
Well, so I'm trying to picture, normally I'm imagining two Wilson lines at the same transverse position.
Yes.
And it cancels with its complex conjugate.
Exactly, yeah. So W times W dagger is equal to 1.
Yeah.
Daniel, you're used to seeing this in word track notation.
This here is, I've just left out the color indices here, but this is ordinary matrix multiplication if I write this as IJ, IJK, KL.
Yeah.
I think the point is if you insert the TA between the W and W daggers, then it doesn't necessarily cancel.
Okay.
This is just not unity. You can easily see that. And if one has any doubt, you could formally expand these Wilson lines in the coupling, and you already find at the lowest or the second lowest order that because the T matrices don't commute, that this gives you some remainder that's different from 1.
Okay, yeah. I think I just was misunderstanding. But yeah, that makes sense.
Yeah. And technically speaking, by the way, if you have Wilson lines in the adjoint representation, for many of the manipulations we did, it was useful to rewrite the adjoint Wilson lines in terms of fundamental ones, then you have twice as many Wilson lines. Looks like a mess in the initial stages of the calculation. But once you have the fundamental Wilson lines, you can write everything, rewrite everything using the color fields identities. And in the end, you get many W times W Dagger terms, and the final result is quite simple. So just a technical remark. It turned out to be much more comfortable doing that rather than taking one of the 50-odd relations between F and D tensors in SU3.
Yeah.
Okay. No, thank you.
Super. Herbert, did you have a question?
Yeah, when you were talking about your subtractions, right? So I have, well, okay, it was a quick run through. I have a rough idea of what you're doing. Now, okay, this is a theoretical definition. Is this easy to replicate in an experiment? I'm the absolutely wrong person to ask this, but kinda.
The thing is, the experimentalist cannot possibly tell the difference between these two.
Right.
And the reason is the difference between these two graphs or representation. I mean, it's the same graph. It's the same graph computed in different ways.
Yeah.
The difference is whether the distance between these two partons is small or large.
Yeah.
And
they can see this, yes.
You can't see this in the final state. It's absolutely unmeasurable. And if you are scratching your head, why can't experimentalists measure a distance? You can convert it into a loop momentum, and then you find this is a loop momentum that runs around this loop and that loop, and never turns out in the final state, and loop momenta are unmeasurable. Which is, in a sense, why if you're very strict, you should tell the experimentalists you cannot distinguish between double parton scattering and single parton scattering at a high loop order. There is something from both in your measurement.
Yeah. So what does that mean for comparing this to data in the end? Are you telling me that there are regions where you expect your theoretically defined observable to nicely match up with what everybody is measuring, and there are regions where you would expect potentially weird things to happen because your definition does not map onto an experimental procedure?
Well, I think
or am I misreading you?
I think what one can take away from this formula here is that this is what the experimentalists can see. And of course, SPS here has many other graphs on top of these. This, in fact, is a loop correction to SPS. It's much simpler SPS graphs. And so you can make this differential, and then certain parts of the SPS will have different signatures, and you can separate them from DPS. The most obvious one was, as I said before, SPS can have these two, the QT of each of these as large as the W mass, whereas DPS cannot. But if you define DPS as whatever is left from the cross-section after you've subtracted single parton scattering computed up to some finite order, then I can say, well, the rest is DPS minus the subtraction term from this. It's not exactly the DPS term, it's this combination.
Okay.
Whether you say, I want to call this DPS or something else, that's nomenclature.
Yep. Okay. Good. Thank you.
Okay. Super. Actually, you answered the questions that I had already. So from the chair. Last call for any questions. And then
I just want to ask about the subtraction procedure. So you put in this cutoff, right? And I'm just curious, what is the sensitivity to that cutoff? It kind of seems like maybe it's canceling slightly because you're subtraction.
Very good question, indeed. So the statement, didn't I even have it? I don't know, I might have forgotten to write it down. What you find is, so you have a cutoff dependence here, And likewise in this term, because this is constructed the same way, only with different functions here. And the difference between these two, the cutoff dependence comes from the small y region. And in the small y region, here, close to the lower cutoff, these two terms are equal, or they're approximately equal, and therefore also how far you integrate down in y, whether to 1 over q or 2 over q or 1 over 2q, should not matter much. Now, in practice, there is a difference between these two because they're only approximately equal, because here you do the full evolution of the distributions. Here you compute them at fixed order. So the cancellation of the cutoff dependence between these two terms is up to orders, higher orders from perturbation theory that are beyond the order at which you evaluate. And that's a familiar statement. You have the same statement about the factorization scale. Yeah. If you vary that in your theoretical prediction, you will find it has an impact, but you know the impact is of the same size of other higher orders that you haven't computed, and therefore it's a part of the uncertainties of your fixed order calculation. By that token, you should find that if you carry everything out to 1 order higher, then also the dependence of the difference on the cutoff should be reduced, because that's then the residual dependence from yet higher orders has been pushed to 1 extra power of r(s). And we're in the middle of a calculation to show that numerically, in fact.
Very good.
Very good. Very good.
All right, super. Well, so thank you very much. I really especially appreciated the pointer to light cone perturbation theory as the way to go for proving factorization theorem. So I anticipate will be very helpful going forward. So yeah, let's thank our speaker one last time.
Thank you very much.
Yeah, and yeah, have a wonderful Christmas.
And enjoy your winter break, your summer break. Bye-bye.
Cheers.
Bye.